So hello everyone. Since this is the very first week, let's just wait for 10 minutes. I'll give access to the rest of the people who have joined for their mics and camera accordingly. Let's just wait for 10 minutes. 6:10 will sharp start. Okay. Okay.
Okay. Okay. Okay.
uh, so this works and this also works. Okay. So I've given you all mic and camera access.
And camera access. And camera access. And camera access.
I hope it doesn't echo now. Yes, perfect. So, hello everyone. I'm Jagriti Patil. I'm a fourth year PhD scholar at IIT Gandhinagar, and currently I'm working with Professor Carla at the Muse Lab, Medical Ultrasound Engineering Lab. So, since it's our very first week today for this introductory mathematical methods for biologists, so this course is like 8 weeks course offered by Professor Ranjit Padinhathari. He's from IIT Bombay. It's like we are only a couple of people over here, countable people, so we can just go through a quick round of introduction. If you would like to, you can just unmute yourself and say about yourself, like which department are you from and what are you hoping to gain from this course, if if it's okay with you. So we can spend for like 2-3 minutes over there, and then we can start. Anyone wants to say something? Uh, Sorry, you weren't audible. Did someone try and say something?
Hi, am I audible now?
Yeah, yes, yes, you are.
Yeah. Hello, ma'am. I'm Aditi,
Right.
and I'm a fourth year medical electronics engineering student, and
Uh-huh.
I'm currently studying in Bangalore, and I took up this course just to brush up my mathematical skills that will be useful in biology, and
Okay.
I really seek to be a neuroscientist in future. So I just want to go through the things already. So yeah,
It's
that's all.
nice.
Thank you.
Thank you. Someone else?
Hi, am I audible?
Yeah, yes, you are.
Yeah, I'm Shweta. I'm a second year biotech student. I'm currently studying in Mysore.
Mhm.
And I basically took up biotechnology because it has both biology and maths. And so
Mhm.
this is a really good interdisciplinary subject for me, and it sounded really interesting. So I chose it.
Okay, thank you. And then we have one more student. Would you like to share something? Okay. So this course is not just like into rigorous maths, but it will also take you from very basics to how it can help you with your experimental methods. Talking about brushing up basics, like as one mentioned here, like Aditi, yes, indeed, because when I was also going through the course contents, I felt that okay, I have forgot about the series. I don't remember the expansion of these things, so it will indeed help you in those things. For a student, so I was a biomedical student and I had this five maths in during our bachelor's. So for me, doing those and learning had a quite a bit. But then now, currently being in a department called as biological engineering, I do have my batchmates who are from biotechnology. So they sometimes do suffer, but they do know this basic skills, and how these helps is like very wonderful. Like sometimes I won't even know how to plot one particular thing that they directly know, because they do this different assays and they have this growth curves. exponential things, and then like they do the cell culture, number of cells you need to seed, how many times you need to check on them. That's everything maths. So how they do these things is very like super cool, and everywhere maths plays a role into. So we'll just go into like we won't go that much into theoretical. We'll start away from seeing functions and expressions, how to see them, but we'll just see like some fundamental things that are always necessary for us to go through into. Like we always have this qualitative research that you see why something is happening and how it feels to, but always you can give it some numbers to throw it to. Like you can quantitatively determine it that how many, how if your hypothesis is true or not, and how to is like people won't even believe that if you say okay my data is good, but what is good data? Good data is nothing. If you say that okay I got 98% accuracy in my data, I had this much sensitivity in my data, the specificity wasn't following through, and then you throw up some percentage against it, then that is a point where they start believing you, start believing your type of research that you're doing. And always it's not that it's always qualitative. You have like this datas are always like differentiated into numerical, and then you have categorical. So one is like this one, this part over here is entirely into quantitatively, say quantitative, whereas the other one over here is qualitative. Qualitative. So one that's like ranking of data and how order of data falls into against if your data is continuous against time, numbers, days, what you're looking through. So if you have a dependent versus an independent variable. So these are some jargon at this point, but we'll go through them one by one. And then you have discrete data. Like if you plot a bar plot or something like that, that okay, at one particular value you have something, then at other particular value you have another thing. So that's a kind of discrete data. Okay, and everything came from this Kerala school from mathematics that was like in the very early 70s, here in India at least, where not early 70s, but it was like almost 1400 to 1600 AD, where people like Madhava and there were Neelkantha, those people in this Kerala school of mathematics, they had established the early roots of calculus. But then later, as we all know, and we have heard about it, that 1700s, late 1700s, Newton came, and then he had to develop mathematics for supporting laws of gravity and motion. So these things are something that okay he knew, but even if you get some time to visit there, it's like in the walls of that particular school you'll see that okay there are graftings of early calculus and variables that you might see, early derivatives, integrals, closed loop derivatives, integrals, those all things come from there. But he was the first one, Newton, to apply them to physical phenomenon and to directly see it. So it has helped a lot of plenty fields. And how you directly say it is that if you have experimental data, and then you what do if you have some so feel free to unmute yourself anytime and say if you have some input. Okay, so when we have some experimental data, it's always better to plot it. So when we plot it, we get a graph, and then graph, this particular graph is nothing but a part of a mathematical function or an expression that it is showing us, right? And these all three things, they coexist together. If you have one thing, you plot it visually to see it, how it is changing, the mathematical function or the expression about it will tell you. So the process goes as that you have a data, you plot it, you see it, so you visualize it, get some trends into it. So how do you get trends? You understand the data, derive some information from it, and see the trends, right? So we have many, this mathematical functions will indeed have some variables. What are variables? These are nothing but some alphabetical letters given to numbers X, Y, Z, A, B, C, can be anything. You can have multiple n number of variables. And against those variables, we have different functions. These variables and functions, how they are related to each other, how they are changing their relationship is nothing but a function. So that expression which relates them, that relates the relationship in between a variable as well as function is the one that will help you observe the phenomenon that you're trying to study. Okay, so you have couple of things, that you have a growth curve, you have temperature, you have those things that you always see in day to day life, that how one is changing against other. So quickly we'll go through some examples of curves that we see. So this is one such example where they do this bacterial growth curve essay, that you seed bacteria over time and you see that okay, how's the growth curve for it. This way it helps you to see that okay, whether it's contaminated or not, whether the cell line, that not cell line, whether the bacteria that you took is healthy, can you further grow it, if the confluency maintained there or not. So in this case they see that okay, and this log number of bacteria is nothing but the number of bacteria, but always you cannot plot it in terms of numbers. Here log helps because it is nothing but order of 10 raised to n order. So that is how you represent log pi. So this is one such phase, another growing phase. Then you have a stationary phase. Then this is a decreasing phase. So here you might see there are some parts to this particular curve. Okay, this one part. In so for now we'll just focus on bare minimal basics, that how it is going through. If someone feels that okay, this things you know, you can jump in and say about it. So this is the phase where it increases, so we can simply call it as an increasing function. Okay, this is a phase where it decreases, so that's a decreasing function. This is a phase where it is constant, you call it as a slope zero. How and where, how will all see those terms. Again, this also constant phase. So that's also slope zero phase. Okay. So these are some terminologies that we have. Now I'll just show you the plots against them. It's locked, I suppose. It's not locked. Okay, there you go. So one such example is this one, that if you have duration of run per day, so this was also used in lecture slides. I'll just use the same ones to help you go through it, revisit it again. So that's minute versus the weight of a person, how it is varying. Now, if you just take Excel, add this fields into, and then go into insert. So I'll just help you with the commands here if you are new to it. Insert and then go into charts or plots, something as that. And there you'll see some scattered kind of thing. With it, there would be some lines against connected like that or something like that. Select it. With respect to it, you'll have a plus sign over here. That plus sign helps you add different features. So this way I've added. So this ones that you see are called as data labels. Okay. This one is axis. So this is your y-axis. So accordingly here my y-axis is weight and x is my duration of run per day. And these are my data labels that I've plotted. What is this called? This is a legend. Okay, so here I've just plotted it. So how it looks to me that okay, as in how the time increases, the person has lost his weight over time. So that's how it's nothing but a decreasing function against time. So following it, we'll see one such function. So here you see another function where you have plotted x and y similarly, all of those things. Now here you see that as in how x is increasing, y is also increasing. So this is a relationship called as y is equals to mx. So that is nothing but where m represents the slope, x here is a dependent variable, y I'll say in some time. Whereas in this case, the dependency not really matters because it's directly proportional to it. Whereas y here is an independent variable. Okay. Now how? So as in how x increases, y changes. Did I do it the other way around? Yes, yes, yes. So y here is a dependent variable which is dependent on x, and x is an independent variable which can change itself. Okay. And the ratio of both of the quantities, y by x, is called as the slope of your term. So in this way, this is the slope. How do you determine slope? That is nothing and in between 2 points and in between two coordinates here, you map it here. So in between two coordinates here. Okay. So y is equals to mx plus this mx is nothing but is a relationship or is an equation for a line that is passing through origin. So this particular point, we called it as origin. Okay. Any doubts still here? This is clear?
Yeah.
Yes.
Okay, cool. Now following it, it's just scaling. So if we see this one, this is y is equals to 2x. So what will happen in this case? Where our y is equals to was x, the first one y1, this y2 is 2x. So it would nothing but it would be scaled by a factor of 2, right? So here also, since it's directly proportional to it, we will have it would pass through the origin, right? Since x is equals to 0, y would also be equals to 0. Since both are equals to 0, it will pass through it. Now, what is the slope in this particular case? Can we find it?
2.
Yeah, exactly. So slope is 2. Compared to this one case, here the slope was 1, right? And this kind of relationship is called as linear, that y is increasing linearly as x is increasing, okay? Now, if we just plot them together, this one line, you see y is equals to x. There is another line, you see y is equals to 2x. So what changes do you see over here? It just scaled by 2 factors. It's increasing linearly, whereas the points, the separation in between those points increase. So that tells us about the slope of 2 over here and slope of 1 being here. So that's the only difference that you see over here. There is also one point that y is equals to mx. Here m, the slope is nothing but for all real numbers, okay? Won't be a complex number or an imaginary number, right? Now there comes this relationship where y is equals to x square. So we know how this comes. This is nothing but directly x square of this particular terms. Okay. Now if I increase x, so till this point it is directly 1. So that would be 1. But when it's like two further iterations of it, when it is 2, it becomes 4, then 3, then 9, then 4 and 16 and so on forward. Now how do you see it? Is this relationship linear?
No, it's not.
Yeah, exactly. So we call it as a non-linear function, because it's not varying with the dependent variable linearly as it has to be, as it is supposed to be. Now, there's also one more thing. If you see y of x, does this relationship hold over here? Can you quickly see that, okay, if I insert x as negative x, is my y same for both cases?
Yeah.
Yes. So that tells us about here. That tells us about symmetry. It also tells us that this particular function, y is equals to x square, is an even function. And sometimes this type of functions are also associated with parabolic functions. That's a different class, we'll see eventually, but these are like different classes to it. So this is a symmetrical, it follows the same across. So it is if you take a bifold across the y-axis, it is exactly the same. It will overlap on its direct replica, the other side of the x-axis. It's an even function. The function of even function is y of x is equals to directly y of minus x. Okay. Then if we scale it, similar to how we did for y is equals to x and then y is equals to 2x, now we have y is equals to x square and y is equals to 2x square. So you see over here, the relationship goes as this. So here also, in earlier terms, it is proportional. Whereas then linearly, it is nothing but it is scaled by a factor of 2. So this kind of functions, it's like now just easy to see and plot that how these functions and their equations vary with respect to time, right? Now, there was one more thing that I wanted to show. I'll see if I have. Okay. Now, if I do y is equals to x and I do y is equals to x square, you see something different here. This is x and this is also, sorry, the y at 0.5 and 1. Whereas after this particular point, it is increasing, right? But before this particular point, it was decreasing, right? So for this particular graph, when we compare y is equals to x and y is equals to x square, where x is less than 1, we have y of x greater than y of x square. And if the other way follows, then it is less than it. Okay, so how come? We'll see here. So when y is equals to x, it increases linearly with respect to x. But when the same relationship goes for x square, because if you insert a smaller number there, the square of that smaller number is even much smaller than that. So for numbers which are less than 1, it would be a decreasing function. So it is less than that. So here the relationship of y of x, which is less than y of x square, follows. Whereas when it increases, the other way follows, which is like well obvious to everyone that okay, this, sorry, the sign's reversed here. Yeah, which we always say that of course the quantity is bigger, x number would be higher there, so then it, the y against it should also be higher. So but we need to be sure about cases which are called as critical points. Against those critical points, our numbers, our limits, the initial values that we are putting at will vary and will cause our data to be fluctuating here and there. This is because there comes rise to noise. If we don't consider these cases, we might end up having noise in our data set. Okay. Then we simply plot x cube. Now here also you see the same thing. See here, then here. So against this one particular point, it is constantly decreasing. So the same phenomena lines over here. Now, how would be the relationship for x, x square and x cube when x is less than 1? Can someone quickly say?
X cube would be the least, then x square, and
Mhm.
then x.
Yeah, exactly. So we have y of x, then you have y of x square, then x cube. It all increases this way. Whereas if it's the other way around, it all decreases this way. Okay. Now, this x cube function, if I have, okay. Now here, you see this function is going around this way. Now, does this relationship hold here? Y of x is equals to y of minus x. Just look at these numbers. Do you have this number and this number same? No, right? We have a negative sign over here. So what we have over here is something as y of negative of x. And this tells you about odd functions, which are not symmetric. So here you see that this function is not at all symmetric and it is not. So if you flip the function against this x-axis, you rotate it over here, you get this particular way. But then that makes your function to be even, which converts it to x square. Now, if you directly flip it across this particular axis, the function will become something like this. Now, this is the antisymmetric part that we are calling it, that it's not at all symmetric. So functions as cube aren't symmetric. Then if you have function as power 4, will it be symmetric? Is it an even function or odd function?
Even function.
Yeah, exactly. So that's an even function. So you have odd powers as odd functions, even powers as even functions, but when you have combinations of them, then you need to look that, okay, which particular function is behaving how. Okay. Then you have one such function that is called as exponential of x. That is also written as e raised to x. So we all particularly have an expansion for this particular exponential series, but there are two things to keep in mind, that exponential power 0 is 1 and exponential power infinity is infinity. Okay, so it comes from Euler's. Uh, I don't know if at this point I should share it, but there is a Taylor series expansion for it, that e raised to x is equals to 1 plus x square by 2 factorial. So I'll tell you what factorial means over here, plus x cube. So it's a directly linear series, but how it follows, I'll say. Okay, and so on. So what is a number's factorial? N factorial is nothing but you take the number n minus 1. Sorry, what am I writing? Sorry. If you have nth factorial, you take the number multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, and so on, continue it further. Okay. For example, if we take 2, 2th factorial. So 2 factorial is 2 times 1. So that gives you 2. 3 factorial is 3 times 2. That gives you 6. Okay. So this is how factorial works. So this is 1 plus x plus s. Now you see What we talked about, this was an independent variable, right? Now, when you're adding this particular variable to 1, will it have a dimension or not? Now, when you're adding something to another thing, you actually want that, okay, dimensions for the same thing should follow. And whether the dimensions follow or not makes your quantity true. Okay, so in this particular case, 1 does not have a dimension. So ideally, this x should also not have a dimension in this case. Now, when you already have terms in exponential, when you say exponential of x, we always talk about the ratio of quantities. Okay, so this is ratio of two quantities, and these two quantities will be similar in nature. Can be time. So if you have time, it can be the time at that particular moment divided by your initial time. Can be length. So your length across something, whereas your initial length. So this can be two variables where it is nothing but dimensionless. Hence, when you have to add a variable that can vary against time at any point, it would be a dimensionless quantity because eventually you're adding it to 1. So these are like some things to remind about the Taylor series and this exponential. Now, for this e raised to x also, there's one more thing that you can always write it as cos x plus I sin x, or the other way around, sin x. Oh no, I guess not the other way around. Cos x plus I sin x. Okay. Now, this x over here in this case can be angle, can be radian. What those are, we'll talk in a bit when we learn about the trigonometric functions. Okay. So, this was all about it. Now, how do you see? So, e raised to x, I told you previously that e raised to 0 is 1. E raised to 1, then the value goes on forward. How do you determine the values to it? Now, this is nothing but it can be written in terms of natural log. How natural log and regular, so log base, you have log base 10, and then you have natural log, which is always base 2e. So we'll learn about this when we learn about log. But for now, if you directly insert into your calculators that exponential of some value, it will give up you this particular numbers. So for now, just stick to this, that okay, it follows this relationship. And of course, it follows the Taylor series. And for following this particular definition right here, you'll need to have an understanding about angle and radians. So you can skip that for now. And Taylor series once is the one that you should follow for this particular case. So if you plot it, it exponentially increases as the name suggests. And that's how, if you do studies as cell culture, growth rate, and those things, the value increases with respect to time. It never decays. It will decay if there is some contamination in your process, but if not, then it will increase over time. Okay. So that was something about dimensionless quantities. I also wanted to say that, okay, now if you say something around here, if my x is way too small, so if it's too small, then my expansion of this Taylor series, this approximates to 1 plus x. I won't go even beyond x square plus by 2 factorial, x cube by 3 factorial in those points. Why not? Because let's say if I have something as 0.1, taking zero point 0.1 square, zero point 0.1 cube, 4, those values won't even give you anything. It will only add up to decimal places. And adding up to those decimal places won't even affect your data to a point that it will cause you any significant variations. So hence, you can approximate to 1 plus x. Okay, similarly, if you have something as e raised to minus x, if I have a plot for it, yeah, okay, I'll have a plot for it. Okay, here. So then I have a plot for e raised to negative x. So what did we see over here? This is an increasing function, right? So it increases as in how the value of x increases. Now what we saw over here, e raised to x can be this one. Okay, sorry, e raised to x is always, e raised to 0 is always 1. Okay, now here, when it is e raised to negative x, the value decreases over time. Then as in how x increases or approaches infinity, e raised to negative infinity is 0. Why? Because we saw that now what would be e raised to negative infinity? It would be 1 raised to 1 by e raised to infinity. And we saw that 1 e raised to infinity is nothing but infinity. 1 by something that is infinity is nothing but 0. Okay. If you apply proper limits to it, it's not like directly infinity to it, but there are limits and laws for it, which gives you an answer as 0. Okay. So it decreases over time. So that's how some negative variable inside an exponential behaves. Okay, so the formula for this also, there's also a Taylor series expansion for e raised to negative x, which is like similar to how you had the first one, but now you remember terms about even and odd functions. Now that was increasing, so it has all plus signs. This is decreasing function, so it will also have combination of something over here, right? So this is nothing but 1 minus, then you have some x, then again you have a plus sign over before your, sorry, even terms by 2 factorial, then you have a negative sign over here. Okay, then again you have a positive sign over here. Okay, so that's how your expression goes on. So that's what e raised to negative x. So here you see that's nothing but a combination of x, x square, x cube, the one functions that we saw previously. Here it was all positives, right? So one way to learn it or to remember the series can be, if it's an increasing function, you'll have all sums of the different order functions that you're trying to see. Whereas if it's a decreasing function, the combinations will eventually have some odd functions, some even functions. And many a times it's being seen that odd functions will be associated with a negative sign, whereas even functions with a positive sign, because positive sign, negative sign doesn't affect them, right? If you insert it. So following it, like there are a couple of examples. So if you see an exponential growth curve, what do you see? You see that in t, like at some time t, you have like n naught, and then after some time t, you have the growth as exponential of to it. So you might have seen this equation many times. So here also this e raised to x, this term is nothing but right here is dimensionless, right? And then there are also like rate reactions where you see rate at particular time t associated at initial time, then you have some activation energy, by you have some rate constants over here. Sorry, this is inside exponential here. So this is your energy, this is also energy, that's also joules by joules. So you take a ratio of them. So always if you see, if exponential have something inside it, that's a dimensionless quantity because it has to be added eventually to one or subtracted from one. Okay, so here also, if the value of x is too small, the equation is nothing but approximated to 1 minus x. Okay, so that was about that. And then you have some functions as sinusoidal functions. So this is, you see this function, the function is like increasing, then decreasing. So you have this different plots against this particular function. Once where it's crossing it, then it's again crossing it, where it's having a maximum value against it. Here also it's having a maximum value against this particular point. Now, these kind of functions, sin x, cos x, these are called as trigonometric functions. Okay. Inside these trigonometric functions, you have, so if you have sine, this is something called as angle or radian. So 1 radian is nothing but, or pi radian, how, so a degree. Angle is nothing but represented in terms of degree. Okay. Angle is represented as degree, whereas radian is a physical quantity against it. So how is the angle that you might, like we see in our early school, that it's length of arc, right, by radius of it. That's how we represent degree by. Now, when you represent degree, we almost say a term as theta. That is in terms of radian, right? So when we take 1 degree, that means it has completed 360 degree of revolution. So that's 1 by 360 of the revolution that it's being taken, right? So when it completes 2 pi, so pi is like half circle, 2 pi is like complete circle, it completes 360 degree. So what is like 1 degree? 1 degree is nothing but pi by 180 radian. Whereas the other way around, if you see, if you want to calculate one, yeah, I don't know if we call it 1 radian. There is something scientific to it. Then that would be inverse to it. So that's 180 by pi degree, right? So that's a conversion in between radians and pi. How you represent it? Okay. Now, here now you know about angle and radian. Now to sin x also, as we saw for this exponential series, it also has its own Taylor series, the expansion to the Taylor series. But for this particular case, the series is now clubbed with, since it's increasing, decreasing, so it's one of a kind of oscillating function, right? So this oscillating function will have a combination of x, x square, x cube, x raised to 4, 5, these orders. But since it's increasing and decreasing, we'll eventually have some plus and negative signs over there. Okay, so you have x because now it's increasing. Then you have negative x cube by 3 factorial plus x raised to 5 by 5 factorial minus x raised to 7. So it's all based on odd. Now why odd? We'll see it eventually. And then plus and so on. Now sin x is an odd function. How it is odd? Because f of x is equals to minus of f of minus x, or how we have been learning till now is negative of f of minus x. So sin x is equals to negative of sin x. It's not always a negative of minus sin x. It's not equal to it. So if you go to table of sine, if you look at even functions in terms of angles, if you see, so at this sine pi by 2 is 1, whereas sine negative pi by 2 is negative 1. So that's like basic example. So in terms of radian, okay, and degree also, if you directly convert it to. So that's an odd function. You don't need to remember these series. But one point that you should know now till now is that you see this particular function. It started from a value from 1, then it ended to a value till 1. Now it's oscillating in between them. It will only increase if I scale it to some value, right? That well, it's not that slope of m, but it can be any value. If I just let's say scale it to some s, so it will only increase. So my sin x is only limited in range by -1 and +1. Okay, so that's something important that you should know, that sin x oscillates in between -1 to 1. Okay. Apart from that, sin x is all about it. And then you have cos x here. That's an even function. So this is an even function. And cos x is equals to cos of negative x. Okay, so it doesn't get a minus sign right over here in front of it. But this particular function, it starts halfway through. Now you saw in terms of sign, it was completely periodic function. The increase, decrease, and little went over here. Now this function does not ever have a negative sign of next to it. So it always oscillates in between 0 and 1. Right? The oscillation for cos x in between is in between 0 and 1. So you see it in between these two values only. Unless and until you pass some negative different x over here, you'll see how the variation increases, but it's always in between 0 and 1, even if it's in terms of angles or radians. Now, the formula for cos x is now, since we saw that it's an even function, so the formula for it follows, and now it's again an oscillating function, increasing, decreasing, will have powers of even order functions. So that would be this one, then there would be plus, then there would be negative sign. Okay, so I hope that's clear till now. Okay. Any doubts till this particular point? Because after that, it's just combination of functions and not more than that. Like first week is always the lighter one that we see. Any questions? And then after that, hi, yes.
How did we obtain those the series, like the
Ah,
Taylor
so
series that you said?
this Taylor series expansion is like it comes from brief derivatives. Even I don't know the
Okay, okay,
derivations for it, but it's like just given formulas. As you know that
okay,
um how do I say it? Okay. Uh, if you know that a rate for one thing is
yeah,
directly, so okay, let's just say um temperature, something into temperature. Okay, let's say if t is equals to t naught times some exponential power next to it. We always know that at t it follows, but at t is always dependent how it started from t equals to 0. So that's like just given to us. For
okay.
likely Taylor series is also like it comes from deep, and even I don't know the
Okay, okay.
derivations for Taylor series. I'll see if I can
Mm,
find something into it,
okay.
but it's not something that you need to learn it. It's just that you
Yeah.
need to remember that if it's an even function, if it's an odd function, if it's an
Mm.
oscillating function, if it's a periodic function, and what are the ranges of values it's flowing through it. But
Okay.
these values are not at all necessary to exponential ones you can always see. But if
Mm.
you start remembering for the sine, then if you start for cos, then comes tan, sec, and all those terms also comes.
Yeah.
So that's not at all needed.
Okay. Yeah. Thank you.
Okay. Okay, so after that, we have the square root. So this is nothing but this one. So that goes like this. So it eventually saturates after a point and then it increases again. Okay, so this is how square root of x follows. Now we'll see how square root of x gives us a variation with respect to x and the other ones. So here, if you see this ones and this ones. So one usually expects that x should be higher. But here also we see a similar relationship as that of x square x cube. That when x is less than 1, y of square root of x is larger than y of x. Whereas when it's greater than 1, the relationship reverses. So if you see in this particular plot where it approaches 1, it is 1, but in cases the square root of x for this particular value is higher than that of this particular one that we had. Okay, so this is like one such critical point for this 2 square root of x and x2. So where in between these points square root of x is higher, whereas after that it is smaller than that. So simple things that we see that okay are very just deterministic they are, and they also do have their own critical points across them. Okay. Similar to it, we have x square. So here also, now x square also decreases, but after a point we see that, okay, it increases. So that's also that, okay, till this point, y is equals to square root of x is greater than y of x square. Whereas after that point, the relationship changes. Okay. Then we have log of x. Now, what is log of x like? Have you previously learned about log? Log as a function? Any one of you? Log base 10, natural log. So log is something, if you say something as y is equals to 10 raised to x, okay? Then you can basically, if you take log on both sides, okay, log base y, okay, it always has a base. Then we do log base 10, then you have 10 here, and then power x. Properties of log say that if you have something to the power of it, that value comes up here. So you have x log base 10 and this. Now if I have an argument as 10 and base is 10, that eventually ends up to be this. So x is equals to log base 10 times y. So this is how the relationship over here comes around. Okay, similarly when we saw the previous one, where you have this one. What will this tell you? So now it also follows something as change of base rule. So now this goes in, this goes out. Sorry. Not that way. Actually that way. So you have e exponential power natural log is 10x x. If you write it this way, y is equals to, should we write it this way? What will it give us? This is e. So that directly, yeah, it changes, it comes here, it tells you about x. So that is directly proportional to x. So these are like some rules for log. Now, if I just give you one example about it. So if I have log base 10 of xy. So this is equals to log base 10 of x plus log base 10 of y. Okay. Now what will happen if they are divided? That is nothing but log base 10 of x minus log base 10 of y. It's not that you multiply it by 1 by y or add it with 1 by y. Okay. Even if you add it with 1 by y, what will happen? The same way, if you follow it this way. Okay. If you don't want to remember many things, if you do it like this way, plus log base 10 of 1 by y. Now what will happen over here? Log base 10 of y raised to minus 1. This power comes ahead, so this gives you like this. Eventually, you end up using the same one that you have previously. Okay. 2 minutes. My battery. Okay, I still have 20% left. Okay, so these are like some derivative, some rules for log. Then if you have something as, uh, okay, this is multiplication, this is division, this is power, this is power. What else is left? I guess that's it. Huh. So you see this relationship for log into Beer-Lambert's law, where you have exponential and 10 raised to power, where you see the rate of lambda with respect to the intensity in and intensity out. So that's how you see log and that nature there. So here's how log also increases. So this is more or less similar to how we saw the previous one, this one, square root of x. So we'll see how both of them also vary, but the shape of them, both of them is similar. So you don't need to remember these terms, but now for log base 1, log base 10, log base 10, and that's 1. This is 0. Okay. And then when you have log base 10 of 10, now these two bases are same. This is 1. So now this varies in between 0 and 1. And in between, you see that it increases. So you just plot it. You see that, okay, this is an increasing function. Log at 0 is not defined. Okay. So you might say that why did we start at 1 instead of 0? Log at 0 is indefinite. It's not infinity, but it's not yet not defined. So log at 0 is not defined. That's not at all infinity. Okay. This is also one more point to look into. Wait. Okay. Then we'll just look at simple series now. So if you have something as, now just how we saw previously, if you have something as 1 by 1 minus x, you can write it as 1 minus x raised to negative 1. That will approximate it to 1 plus x. This minus 1 goes into this power, so you can write it as 1 plus x. Now the relationship for it also goes as 1 plus x square plus x cube and so on. But you don't need to remember this series. Usually you get series like this when this is in denominator, when your x is too small. When it's too small, just remember the when x is too small, how it approximates to. So that's how the relationship goes as. Whereas if you have the other way around, this way, where you get 1 plus 6 like this will approximate to 1 minus x. And that will also be like, now this we saw that it has a negative sign next to it. So it goes as this. Okay. Plus, huh. Okay. So here we see that this function is increasing. This function is decreasing. Right. Now this function increases with value of x. This will eventually decrease because, and both on this particular functions, if x is infinity, they'll eventually turn out 0. Okay, so they'll go as 0 as in how the value increases, both the functions. Then we had y is equals to square root of x that we saw previously. 2 minutes. Okay, chat space. Okay, so we had this decreasing functions. Now with decreasing functions, I had an example to show to you. I just forgot about it. Okay, but the one that I remember now is something about, I don't know if you all remember, this is something about Gibbs free energy. Okay, and that goes something as this. Okay, yeah. But this is free energy, Gibbs free energy. This is your enthalpy. This is temperature. And this is entropy. Right? Now, this tells you about the order of randomness. This tells you about how much heat is being absorbed or released. This tells you about the energy into the system if it's spontaneous or not. Most of the time, if it's spontaneous, that's less than 0. If it's at equilibrium, it would be equals to 0. And if it's greater than 0, it's non-spontaneous. Okay. So in real life systems, it is highly ordered, highly random, unordered. So for it to be highly unordered, this delta should be higher then this delta H. So when it should be higher than that, that means that this should be very highly positive. This can be negative or should be less than that particular value for it to be a spontaneous system. Now, for a spontaneous system, when there is high order of randomness, this function or this type of energy is always a decreasing function. Okay, so I guess that example makes it up. After that, you also have something as, okay, when you do bacterial cell culture, I don't know how many people here would be aware with it, but when you culture it, the number of bacterial cells increases, whereas the nutrients or the concentration of the nutrient that you put it into decreases. So the concentration of nutrient that you're looking into is a nothing but a decreasing function. But this is relative to the cell number over here, right? Because overall, for the bacterial growth, you want the nutrient to be again, you pour it in, you change it, refresh it again. So that's how the function increases. So in real life, you do see many increasing and decreasing functions. But for now, I guess this should make up. Do you have any doubts? If not, then we'll go for this free week assignment question. And then I guess that's it for today. Do you have any questions? So for plotting, you can always use Excel or you can use a graph plotter, that's GNU plot. But I'll just show my screen to you. Okay, I hope my screen is visible now. Yes, it is visible. Then if we look into course, so this is one JNU plot that the professor has advised to look into. He'll eventually show how it works. But if you want, you can just go through this demos and try and download it. It's very like less heavy package, or else like nowadays Excel has also much more advanced. Then you also have different packages as like MATLAB, Python. You can also plot through them. But here also it makes pretty good plots that you can directly use in for your publications or presentations. You can also import files that can be added into this n number of extensions. So it supports through Windows 11 till now, and if you want to use, you can always try and see. I haven't downloaded it yet because I was waiting for its Git repo. My system only supports Linux, so I'm waiting to download this particular version and see how it would be. So you can always go through it. That's GNU plot homepage. Okay. Let's just see the assignment now. 26. Yes. Hmm? What is this? 2 minutes. Hmm, I don't know what's happening. Share. Okay, it's not currently sharing. Do you guys see my screen? Yes, I should be
I
able to
can't
see
see.
something on my screen. Yes. Is this visible?
Yeah.
Yes. Okay. So this is from last year. That will help you solve the assignment that's due today or tomorrow or something. So we'll see the questions side by side and we'll look at the answers next to it. Okay. Okay, so yeah, see here there's a question that what happens to the coefficient of cos x when it's a 1/5 term of this x raised to 4 in the expansion. So for this you need to know the series of cos x, but that's just cos x, not more than that the function. So you have one negative exponential, then you don't have any other ones. Yeah. So sine and cos are something that you can always look into. So now they are asking about the 1/5 coefficient. So increase is 1, 2, 3, 4, and then again fifth one. So that would be this one of x raised to 4 in this particular expansion. So that is 1 by 4 factorial. 4 factorial would be 4 times 3 times 2 times 1. Okay, so you just do that's 1 by 120. Okay. The next question is which of the following is an even function? So we see this x square plus 1. So again, this one function is also you have plus 1 against it. Then you have cos x plus pi. Pi follows it, but pi is a constant. So cos x is a even function that we know. Log won't be defined and we cannot be directly multiplied to it. And then you have both a and b. So this is a constant function. This one is also a constant. So both a and b are even functions here. Okay. Then, if you remember the series for this one, since it was an odd function, we had an alternating sign since it was oscillating here. So, this is minus x plus square, then negative, then positive. So, for x cube, it is nothing but 1 by 3 factorial, that's 6. But bear in mind the sign matters. So, whenever you do questions like this, beware that you need to add enter like see the sign against it. So, that would be negative 1 by 6. Okay. Then there's a question which is a non-periodic function. Non-periodic as in which is not symmetric, whereas but not symmetric doesn't even follow. It can also be an odd function against it. So this over here, x cube is a non-periodic function. Now why? Because it does not repeat its same similar nature after time. Cos x does repeat, sin x also repeats. Whereas x cube, it will keep on increasing, keep on decreasing, but it won't repeat the same function or same nature after some point. It will keep on doing the same thing. It won't repeat after its point. It won't cross zero after a point. So that's why it's a non-periodic function. Okay. Then for logarithmic expansion, if we see log of a base a, this is a, that's wrong, right? Because it would be 1. Log of base to an argument, it would be a 1. Then natural log, you cannot write it in terms of base 2. If you have product of two terms, can be written as the other way around, where no, this is wrong, because you can write it as log of this m plus log of the base plus n. You can write it that way. Then you have log base a m raised to p. Then p goes out, log base a, and then m. So that's the right way. So option 4 is the correct one for it. Okay. Then sixth one, you see that which of the following identity is true. So for this one, you need to know about inverse functions. But even if you don't know about inverse functions, just see over here that we now know that sine is an odd function, right? And tan and cot come from each other. So that both of them are like inverse of each other. Now tan is nothing but a what do you say, a ratio of sine and cos. Now sine and cos, there is one odd term, there's another even term. So that eventually would be an odd and even combination would be an would be an odd that you're looking for. But one is inverse of the another, so this ratio won't hold true. Whereas if you see, and again, the negative sign inside of them are following the negative, positive signs that are again to the right hand side of it. So both these expressions are incorrect because the relationship goes as x to negative x. Similarly here also goes from x to negative x, whereas here you have an against extra term of pi. So this one is the only option that is like following x. Sine inverse of negative x is equals to negative of sine inverse of x. Okay, so that's the following identity that we have. If you all are like very new to trigonometry and functions or might have learned it early days in school, you can just go into like see basic functions of trigonometry, some identities like you have sine square plus cos square is 1, then you have sec square minus tan square is 1. Those kind of functions you can see what is the inverse of another function is like now we saw that how sine and cos varies. You can try and see the plots for sec, you can try and see for cot, cosec, sec. Those functions you can try and see how those vary and the relationship in between them. If not, next time I can also share a table how different trigonometric identities vary. Okay. Then now this one you have, I guess, if yeah, there's a plot for it. So you have two functions, y is equals to x square and negative x squares. If we go along x-axis from origin, predict the nature of the differences in between these two curves. What will happen? So if you see here, now this one we plotted x square and negative x square would be directly inverse to it, like directly flipped on the x-axis. So it's directly by this way. Now what's happening to both of these curves? The values in between these curves, the difference in between these two curves. So that is nothing but this, if you say it as y1 and this as y2, the difference in between y1 minus y2 is like constantly increasing. So that's an increasing function. Okay. Now, which of the following has a value of unity at 0? So that we saw that, okay, this one has, this one has, this one doesn't, because sin x is 0, cos x is 1, e raised to 0 is 1. Okay. Then which of the following functions have value 0 at infinity and negative infinity? So a value as 0. So if we see over here, e raised to negative x, we have 10x that will increase. Tan x has a, so tan x, the graph for tan x goes as this, similar to your x cube. I'll show you here. So if you, how we saw for x cube, the values kept on increasing. So the tan x graph is also like this. So it keeps on increasing. It will never intersect it unless and until it's a pi. Okay. So that rules out. Then we have another option is e raised to negative x. But it won't hold true at infinity and negative infinity, both of them. Only at negative infinity, it would be 0. Okay. Then another function is x by 1 plus x. That will hold true, but here you have x here. If it was 1, then it would have been 0 in this particular case. Last option, you have e raised to negative of mod x. So whether it's plus infinity or minus infinity, at all times, it is giving you e raised to negative infinity. And e raised to negative infinity, we saw that it is 0. So hence the answer is the last one. Okay. The last question, I guess you all can try solving this question, how it comes to this. So imagine that a protein has some finite concentration. This units at a time, the concentration decreases exponentially with respect to time. So what's an appropriate mathematical function to represent it? So we just wrote that L is equals to L naught times e raised to minus t, and where that t is also nothing but ratio of two quantities. So that would be time quantities, because here we have this particular value at time t equals to 0. So something which is here in like exponential power, it is also ratio of two particular things. So that would be e raised to minus t by t naught would have been the correct answer. But in this case, if they have not written, this is the one that is correct answer. Now, why it is negative t? Because they have told us that it decreases exponentially. Okay. If it would have been increases exponentially, then option B would have been the correct one. Okay. Do you have any questions on this ones? Because this will help you solve the assignment that's due today or tomorrow for this current year. If you have any questions, you can let me know. Yeah, that's it. So we went quite fastly today because it was just basics here that we're looking at. Following weeks, so week 2, that's like coming up Tuesday, we'll look at function derivatives and derivation of curves. So I can help you guys with trigonometry. If you had like problems or you felt that my pace was too fast or something as that, you can let me know for this current week. Accordingly, I can adjust my pace for the further week that will will meet on next Tuesday. That would be 3rd Feb. So do you have any questions? Meanwhile, I'll also share this recording that we have done. It would be shared with you via YouTube, and there would be an Excel sheet through which you can track each week's recorded session and the assignments that have been shared. Also, the notes that we have been taking. So, all of this stuff would be uploaded online, and the links for the same would be given to you. So for that, you can like directly access here in some part of your course, you will see as online recording or online session, something like that. And there you can get an Excel sheet from there. So you can look into it. I guess I do have here, I don't have, but yeah. So there you can directly access what we did today. Okay. Do you have any further questions? If not, then we are done for today. Thanks for joining.
Thank you so much.
Thank you. So Utpal, thanks for joining. Do you have any questions? Okay. So if not, I'll be closing the session. Thanks for joining. We'll see you next week. Okay. Thank you. Bye bye.